So, I will demonstrate this photoelastic constant of a crystal, that experiment. So, this is the setup of, uh, of that experiment in our optics laboratory of Department of Physics, IIT Kharagpur. So, you can see, just I have said that experiment, and the fringe as I discussed, that I am showing you in a mobile camera. So, these are the fringe, dark bright, these are fringe, and this is the crosswire, this is the crosswire. Okay. So, I will explain everything, So, but before that, here, so what we have to do, we have to measure the fringe width, as well as we have to measure the fringe shift. Okay. So, first fringe width we can measure, So, I think dark fringe are very sharp. So, we will take reading, say let us start from here. Okay. So, this, let us take this one. Okay. So, this say fringe number 1. So, what is the reading? How to take reading, I will tell you. So, note down this reading. So, this is first one, then I am going to the second dark. Okay. Take the reading, then third dark, third fringe, take reading, fourth fringe, take reading. Okay. So, this way you take reading of, say, 8 fringes, 8. So, then note down, here I have table, So, fringe number 1, 2, 3, 4, 5, 8. Then reading, we have basically main scale and vernier scale. I will show you, since I have set up, and then I do not want to disturb before explaining you. So, main scale reading, vernier scale reading, there is total reading. So, here you are getting the reading of each position of the fringe. So, now calculation you can do, actually calculation generally what we do, since this fringe width is very small. So, you have 8 fringe. So, basically you take difference between 1 and 5, then 2 and 6, then 3 and 7, then 4 and 8. Okay. So, in between, so 1, 2, 3, 4, 5. So, in between how many fringes are there? So, 1, 2, 3, 4, 5, right. So, this is number 1, this 2, this 3, this 4, this 5. So, how many? 1, 2, 3, 4. Okay. So, you have to, what is the difference you are getting, and divide by, so then take average of this basically 4 fringes. Okay. And then divide by 4, that will be the fringe width. So, that one can calculate. Second, we have to measure the fringe shift, okay, for different weight, as I told you. So, we will put different weight, and corresponding fringe shift we have to measure. Okay. During loading the weight, we will take one set of reading, and during unloading the weight, we will take another set of reading. Then you can take average of during loading and unloading for corresponding that weight. Okay. So, then you will get basically fringe shift S, that you have to so that from this reading itself you will get this fringe shift. Okay. So, that I will show you how we will do that. So, fringe are there. Okay. So, what I will do, I will set it just middle of this. I think I will set it this middle of this bright fringe, then you can see the crosshair. So, I have set at the middle of this one bright fringe. Okay. Now, if I put weight, here, we have basically here here I will explain you. So, now I am putting weight, just I want to show you here. So, I am putting weight, there is a slot here. So, I think I half kilo weight I put, okay, but not much change. Then I am putting the, so 1 kilo weight I have put, okay. So, there is a shift. So, for this 1 kilo weight, what is the shift, that to find out, basically now I have to note down that initial reading of this one. Now, I will change this to bring it back in middle, okay, to bring it back to middle, okay. So, now what is the reading I have to take, okay. So, for this weight 1 kilo weight, 1 kg weight, what is the fringe shift, okay. So, that fringe shift I calculated from this one. So, now initial reading you have to basically keep note down with unload switch condition. Now, for different weight you are changing and bringing bringing back at the center, okay. And then for that, what is the reading you have to note down, okay. Now, again I will put weight, 1 kilo more weight I will put, okay. So, now is basically 2 kilo weight, 2 kilo weights. For that again I will bring back to the middle, So, we will change the weight, and there will be shifting of the fringe, and how much shifting of the fringe for weight. So, that to bring it back to the original position. So, that there will be change of the reading. So, we have to basically note down those. So, we will basically put weight for that. So, for 0 weight means when unloaded. So, what is the, I think yes. So, what is the reading we have to take, okay, and then we are putting weight, and then there will be change, there will be shift to bring it back. So, we are changing it, and how much. So, there will be change of the reading. So, that reading we have to note down, okay, during loading, during unloading, okay, and from there this shift we have to find out. So, as I so here you can see this, if we just using my hand, if I put just some weight, you see the shifting of the fringe, okay. So, yes, so I am putting stress, and then they just, okay. So, so this is the weight, we have many weight. So, I am not putting them all. So, just change weight of 1 kilo. So, up to I think you can give 8 kilo weight, okay. So, 1 kilo, 2 kilo, 3 kilo, 4 kilo. So, that way you can go to up to 8 kilo, and then you again unload it, during unload I will unload 1 kilo, I will unload 1 kilo. Okay. Okay. So, during unloading also there will be shift of this, and then you should bring back to this and then take reading. Okay. So, this way during loading, during unloading, how much the shift is there. So, with this Babinet compensator, that shift we can measure. Okay. So, whatever I am showing here, so that's the, it's a slightly difficult, slightly difficult to catch in camera. So, it looks very sharp and better. So, there precisely you can see. So, now I will show the different parts of the experiment. So, now this is the source, this is the sodium source, yellow light, sodium D1, D2 basically. So, now this is the lens, convex lens. So, this light from the source is falling on the convex lens, and we have adjusted the distance in such a way that it should be more or less at the focal point. Okay. So, parallel rays we will get from the other side. Now, this is the polarizer, okay. So, here indicator you can see, here indicator one can see I have placed it more or less at the 45, 55 at this angle. So, now this is the axis of optics axis, okay. This is the optics axis. Now, the polarized light will come and this optics axis. So, this basically the electric component will be in this direction, So, here is a small slit is there. So, just to select the light width, basically to select the light width and length. So, these are so now plane polarized is coming, plane polarized light is coming as if this is the now slit source, this is the slit source. Okay. So, plane polarized light are coming and falling on the crystal, this type of crystal as I showed you, this type of crystal we have fixed like this, and then this part is basically it's like this, okay, it's like this, okay, it's like this, okay. So, that cantilever, that force applied here the sharp edge, and that force will be put here, we clamped here. So, it will be put on the area of this one BH. Okay. So, initially there should not be any weight, or some preliminary weight can be maybe there. Okay. Okay. So, generally we tell the dead weight. Okay. So, this weight generally you can also take it away. So, some weight are there. Okay. So, this we tell this is the dead weight. Okay. So, that means for this small weight, so there nothing will happen, no stress, that stress is not enough to make it anisotrope, okay, anisotropic. So, it's a similar as the unstressed one. So, this is the unstressed condition. At this condition, now light will come, E ray and O ray both will have there will not be phase difference between E ray and O ray. Okay. So, now that are coming, this is the Babinet compensator, Okay. This whole part is Babinet compensator. So, basically this type of arrangement is there, this type of arrangement is there, you see this part. Okay. So, one part is this, you can see this crystal, okay. It's a half is half, one half from this and another half from there, okay. So, although it is a rectangular one, but one half is active and another half is passive, okay. So, here the other half is active and uh, another half is passive, okay. So, this part is fixed here, we will put this way. I think there is a marking, we have to, yeah, there is a marking, we have to put this way. So, this part will be fixed and this part, when I am rotating this one, basically yes, you see this half is going this side, this half is going this side, okay. Other way I am rotating other way, okay. Okay. So, it is moving. So, this as I showed this, one half of the crystal, one half of the crystal will fixed and another half of the crystal is moved. So, how much it is moving, that we can take reading from here. So, here there is a, here you can see, so this basically here probably I cannot show you, but now you see here there is a scale here, okay, linear scale, there is a scale here, linear scale. So, there is a marker here 0. So, initially we will put at 0, I will put at 0 of the main scale, it is the in middle, I can see it is in middle, yes, okay. So, that time this is the basically circular scale, this is the circular scale, here you can see this is the circular scale. So, circular scale, these 100 divisions are there. So, this is 0, this is 0, if I rotate this, then 10, 20, 30, 40, 50, 60, 70, 80, 90, 0, okay. So, then for one complete rotation, here this scale, this one moves by 1 millimeter, okay. So, that means the least count or Vernier constant, you can tell 1 millimeter by 100. So, 0.01 millimeter, okay. And this other one basically here you can, here there is option. So, you can this tilt, you can adjust this tilt, yes, you can see this, it's a coming this way, okay. So, other way I will go. So, this basically to adjust the tilt, this one. So, now this is the Babinet compensator. So, here you can take reading how much you are shifting the one half of the compensator, Babinet compensator, okay. And then here this is the basically another polarizer, this we tell analyzer, okay. So, here as I told, depending on the position you will get dark bright this kind of things, okay. So, here another one. So, here if you see the position, this is at 55 and this is at other side, okay. So, it generally we keep, so that we adjust, and generally if we keep at 90 degree cross position, 90 degree cross position, generally we get better what I should tell this the fringe it's quite distinct. It's quite distinct. If you use this one, if you don't use this one, then it's not the fringe is not that sharp. Okay, so this cross position is basically it's a make sure that so at dark position it will make it dark, it will make completely dark. So at cross position when they are out of phase, when there it may happen it's in cross if it is in I think same direction, and if there is some rotation, okay. So you will not what you will get, you will get some component of the of that electric component along this, but if you keep at cross position, so basically this I think that dark part will be more dark and bright part will be more bright. So the sharpness of the fringe will enhanced. Okay. So that is the purpose of this polarizer, which is acting as an analyzer. Okay. And this end of this polarizer here, this basically eyepiece is there. Okay. So this kind of eyepiece are attached, this kind of eyepiece is attached here. Okay. So basically polarizer analyzer, this kind of same kind of, so here there is a arrangement to insert this eyepiece. So here we have put eyepiece, and through this eyepiece we can see the fringe as I showed you in mobile camera. So now this whatever I told you, just see and just first measure the fringe width. Okay. Take reading 1, 2, 3, 4, 5, 6, 7, 8 fringe, setting at dark, okay. Take the reading from here and then come to the next part for putting weight, So yeah, I think this is the eyepiece, crosser also there. Okay. So I think yes, yeah. So this way actually we have inserted at this like this. Okay. So there we don't need, so here we have put here inside this. Okay. So so next task is for just for different load, for different mass or weight. Okay. We have to take reading of fringe shift, and that already I have told you. So this experiment is very simple and beautiful experiment for measuring the photoelastic constant. So here we have that one direction, we are putting the stress in a particular direction, say this the some x direction, and light is propagating along the z direction, okay. So polarized light, it is on the xy plane, so it will when it will enter here, so it will have two component, one is I think this, another is this. Okay. So one will act as a E ray and other one will act as O ray. Because of this stage, this refractive index for O ray and E ray will change, and then it will introduce path difference, phase difference. That path difference, because of that path difference or phase difference, there will be shifting of the fringe pattern formed by this Babnet compensator. Babnet compensator. Babinet compensator. So So, that fringe we will observe and see the shifting of the fringe as a function of weight. So, function of weight, that is by using the cantilever technique, we are applying the uh, uh, force or stress, that effective stress will be more than the weight we are putting there. So, that fringe will see and will measure the fringe width as well as fringe shift. So, these the so whole things, it's basically this you can also see that how to use Babinet compensator for measuring the phase difference between two rays. Okay. So, these are very useful tools for measuring path difference or phase difference between two rays, and how it can be done. So, that we have shown. I think after that you have to plot graph, as I told. You have to taking reading. After that you have to plot weight and this shift. From there you will get the slope, and from their slope you will get the photoelastic constant. Okay. So, I think this is a nice experiment. I will stop here. Thank you for your attention.